I think probably everything will settle. So I'm going to talk a little bit about our efforts on bringing IOTA on the Ledger Nano, and this is not going to be a demo because as this is a developer meetup, it's more going to be about the software development difficulties that there are and why this is much harder to get IOTA working than, for example, every other Bitcoin clone there might be. So just to know where I'm at, who knows what the Ledger Nano is?
Nope.
Okay. Who owns a Ledger? Ah, awesome. Okay, I think I'll still start with a brief introduction about what hardware wallets are in general, because the Ledger Nano is a special kind of hardware wallet, and then we get into the Nano and IOTA specifically. So basically the idea you have for hardware wallets is you want to isolate all the cryptographic secrets that there are. You want to isolate them on a different device, because when they're on your PC or your laptop or whatever, they could get grabbed by keyloggers, viruses and stuff like that. So if you keep it on a separate device, this is usually secure, and for that the device needs to be somehow tamper-proof, and also it must not be possible to somehow extract the information from there. And this is why it usually have a specially hardened secure element. Another thing that usually come with is a true random number generator, because for all this cryptographic stuff you need random numbers. And if you do this usual pseudo random generators, there might be some issues with it, so it's just always good to have a true random numerator there. And then you keep the keys always on this device, on this hardware wallet. And that means if you want to generate a new public address, then of course the corresponding private key is kept on the device, and only the public address gets transferred back. And for transactions, it's also kind of similar, because the transaction, you make it maybe on your PC, and then you transfer it to the wallet, and it's signed there, because it can't be signed on your PC, because that would mean that the private key had to left. And then the signed transaction comes back and can be used. And for that, this is not safe against man-in-the-middle attacks. So for that, usually those hardware wallets have a display, and they say, do you really want to transmit this amount to that address, and you confirm there to make sure that the address you're sending to is actually the same than you had in your PC. And usually also they come with PIN codes, so even if you lose your wallet and someone else finds it, he can't use it, because it also needs an additional layer of security for that. And so now the question is, what happens if you lose this wallet? Is then all your funds gone? And the fortunate answer is no. Since a couple of years, we're no longer in the dark ages of Bitcoin, and there's something like called hierarchical deterministic wallets, where basically everything starts with a certain seed. This is usually represented by this so-and-so mnemonic words, and then a seed is derived from that, and then certain mathematical functions are applied upon this seed. And so that you can use this what's called a path, so that for different currencies, different addresses, different accounts, different purposes, you can derive own addresses or own subseeds, and they're deterministic. So if you enter the same seed, no matter on what device or whatever you use it, is going to produce the same key, the same seed. And so you can always reinitiate your ledger, for example, if you still have this initial recovery seed, or you could even use a software wallet with that seed and produce the same addresses, the same keys then for your ledger. And this is how I said how a transaction would look, for example. They are signed on the device with a private key that is only known there, and then they need to be confirmed on the device, and you can see that in the picture there. You have a transaction of so and so many Bitcoins, and you can say yes or no. If you say yes, it is signed, transferred back, and then the computer can work with that. Okay, now we come to the Ledger Nano. So there's a picture again. It is USB based. It has an OLED display and just two buttons where you can, usually if you press both of them, it's confirm, and left and right is going up and down. and it is special hardened security environment. The guys behind Ledger called it BOLOS. And so what does this actually mean? So it uses a hardened secure element. This is a standard ship that is used for other security relevant purposes. And those, and this ship, for example, they usually don't come with any I/O because they need to be hardened and stuff like that. But you want to write basically apps for that. And to make that possible and still secure, the Ledger guys decided to put another, basically, router before that. So everything like buttons, the USB, the display goes through this router chip, and only if it passes the firmware there, the events, the commands come to the secure element. So this is also make sure you can't just install any software on it, or you can't just extract data, because everything needs to go through this router. And it also solves the issue that from a technical point of view, the secure element doesn't have any IOs. It just communicates with this router, and this router has standard ports for USB and stuff like that. And what they do then from the software point here, they have some operating system. But this secure element is really limited computational wise, so it just can one application at a time. And it can be either system mode or user mode. And all the regular applications or the wallet applications or whatever are user modes. And they can't do the cryptographic relevant stuff. For that, they need to initiate the so-called syscall. Then it gets transferred into system mode. The BIOS or the OS takes over, verify this command. So for example, if you want to derive a public key with respect to a certain path, it checks whether your application is actually allowed to use that path. For example, if I write an application for the Ledger that just asks, give me the first Bitcoin address because derived from this path, then it would not allow that because it knows you're not the official Bitcoin wallet, you don't have the signature for that, so it would deny this request, and you can't use that. So those calls get verified there, and then again it's transferred back to the application, so that in the end only one application can run at a time. And also it has some cryptographic coprocessors for the true random number generator, for example, and some hash functions are also implemented in hardware. And for that you also need to do a syscall to get to this, upload your data there, and then get your results back. And this is basically what separates the Ledger from other hardware wallets, for example, like the Trezor. The Trezor is just an isolated little computer. It doesn't have this security precaution. It runs everything. It just is just a separate tiny computer, but it doesn't have these additional security features which the Ledger has, and which it allows to really write apps or applications for the Ledger that are still really, really secure. And this is what this BOLOS, this blockchain open ledger operating system does, and where the Ledger company is pretty proud of. So, from a software point of view, you're supposed to write embedded C code. It is an ARM processor, so you can compile it with an ARM compiler. The code you write runs on the secure element. So the router is a much more potent regular ARM chip, but you're not supposed to change it because it's just the router. Your code runs on the very limited ST31, and this is really slow. It just has, to make it a little bit better, support for certain crypto functions in hardware. But apart from that, it just has a total of 4K RAM, and this is even a little misleading because of those 4K, 1K is a stack. You can't really, this is too small to use for any stack variables, and too big to come for other things. So, and there's certain global variables that come with the system. So, more or less, you can assume you can work with 2K. So, 2K is all you can work with. And then you need to write apps that can work with these limitations. And then for that, they have an SDK and a Python loader. So this is pretty convenient. You can just make your make load, and then the Python loader kicks in, uploads everything to the ledger. There's also some cryptographic process in there, but this Python library all does this. So it gives you a key, and you just need to say, okay, this key is allowed to change my ledger and stuff like that. And then it uploads the app to the ledger. And this is even it's actually not a security problem because it can't get to any cryptographic relevant functions. So I still would not recommend if you go on GitHub and just upload any ledger app you find there on your ledger. I still would not do that. You should be really, really careful what you do there. And if you do it, you should use the option. They have an option for a second passcode. So basically, you can access, you can enter a different passcode, and then the seed changes completely. And then you can use basically this new seed for your installed apps. And then even if something should go wrong, they are not able to access your seeds of your main account. So just as in here. Okay, now a little bit about the project history. So you can find it in GitHub under this address there. And basically, we three are working on it, and it was kind of funny because around Christmas, we were all working on this independently, and then early this year we decided to put everything together and work together. And Peter, he was the first one. He posted something on Reddit where he showed a photo of an IOTA address generated on his ledger, and that actually gained a lot of traction in the IOTA community. So he also has some nice blogs about that and stuff. So he did a lot of PR stuff, and he was mainly working on the in the I/O part, and actually working, getting the interface and everything running on the ledger Nano. Then Diskins or Tyler, he was also working on that on his own, basically. And I was also working, I was just at that point only focusing on the pure C part. So I was basically interested to get a very, very lightweight C implementation of IOTA running. I wasn't at that point bothering with this ledger stuff. I just had the limitations in mind. So it actually fit together pretty nicely because we could then combine it and our efforts there. And so there is no real working C implementation for that. There is a more or less working version for the Trezor, and what the guy behind that basically did, he more or less ported the JavaScript code, the official JS library there is, that more or less works, but of course it wastes a huge amount of memory. It works if you have a decent, any decent hardware, it's absolutely fine to work with this, but for the ledger this is completely futile, because you just have so many limitations concerning speed and RAM. So we started initially to use that as a basic, but then we had to change so many things to get it running on the ledger. And yeah, so this is our current status. So basically, what you want to do is you want a C implementation of IOTA using 2K of RAM. And this also has other limitations. You don't have the full standard libraries, you don't have a heap, you don't have malloc, so usual embedded limitations there are. And so actually it kind of fits nicely in about the last points we had that were raised here for the last talk. So IOTA, as most of you guys probably know, uses balanced ternary system. So my background is in math, and I must say I really understand and I enjoy the beauty of this, but it's just, it is a pain if you want to do it on a really low power hardware. So what it does is you have your number system with a basis of 3, but not as you'd usually do with 0, 1, 2. You have it balanced with -1, 0, and +1. And this has the huge advantage that you don't need to make any distinctions between signed and unsigned data types. So in binary, you always have this issue with signed and unsigned and how you represent signed numbers. You don't need to do that if you have this balanced system, because it comes with negative numbers built in. And also from a mathematical point of view, it is more efficient, more space efficient than the binary system. But still, there is no hardware that supports it. You need to emulate it in bits. And so here you have your trig with the 3 values, and then what the rest is more or less, it's IOTA specific notation. The usual notation is a little different, so people that don't quite agree on what a trit is, whether it's 3 or 9 trigs, but for IOTA it's clear. A trit, I'll denote that with a capital T, so on, is 3 trigs, so it has values from negative 13 to positive 13. And they usually encoded base 27, so those are all those texts you see when you look at a IOTA transaction. So starting with n corresponds to negative 13, going all the way, 9 is 0, and m is the largest value with plus 13. And they encode everything in Little Indian, so basically the least significant trig comes first, and then you go down up to your most significant bit. Trig, of course. And now, how the hashing works. They currently use what they call curl. If you guys recall, there were some issues, I think in November or December, where they had to, or where they replaced the original curl implementation they had. And this was their own version. So it worked, it was designed with having Internet of Things and small hardware and main, and it was actually based on the ternary system. And they completely replaced that with curl or whatever, which is basically tries to do the same thing but a more established regular hashing function. But this, of course, works on binary, no longer on trigs. But they wanted to say the chunk size was 243 trigs, so they wanted to stick with that. And now the issue, the KEKAK has just 48 byte hash. And if you do the math, if to encode 243 trigs, you need 386 bits. And this is unfortunately 48 bytes and 2 bits. So it doesn't fit in the 48 bits that the hashing function is working with. And so what they said, okay, we just ignore the last trig. So we basically always set it to 0 before putting it into the hash function. Then we have a smaller number. This can be fully represented in 48 bits. And the result we get out, this might have still some undefined values for the 43rd trig. So we set it back to 0 again and use with that. That's how it is. So, and then to convert it, they use the 48 byte representation in 2's complement in big endian to transfer the ternary number into binary, so that then the regular binary hash function can work on it. And so if you just do the math, an address is just the result of one hash. So it is 243 trigs. And if you encode it with the default base 27 encoding, that corresponds to 28 characters. A private key is for security level 2. So there are those 3 security levels, 1, 2, and 3. 2 is the default one, so I put the numbers for 2 down here. Is 13,100 trigs. But you don't need them. So what actually is, for each 243 trigs, you just need 48 bytes, because the rest is discarded anyways. So if you apply this, you can at least get this down to 2,592 bytes, which is still more than we have, but it's the best you can do. And it even gets much worse for signatures, because the private key is just kept on the device, so we can basically encode it any way we want it. But for the signature, it must be transferred back to the host in this usually base 27 encoding. So that would make 4,000 something characters for level 2 security. So this is an issue you need to address on the ledger. And internally, what we decided to do is we are basically working on 12 unsigned 32-bit numbers. This is exactly then those 48 bytes, and you can work most efficiently on those because you need to do those big integer arithmetics on those. You need to add them, whatever. So this turned out to be on the ledger the most efficient data structure you could have. But of course, you always need to convert them back to trits when you want to transfer them out. Okay, so how can we then generate public addresses? So for a public address, it's just the hash of your private key, and the private key is generated from seed and the address index, it's called. And this is actually not an issue. It's not so comfortable as it is for Bitcoin, let's say, because the built-in functions for the ledger, they can give you a certain Bitcoin private key hardware. You just say, I want the key corresponding to the following path, and it returns it to you. And this is the only way you can actually access the seed on the ledger, because you're not supposed to ask what is the initial, the seed entered, because this would be a security risk. You can only say, I want it derived from that path and for that cryptographic algorithm. So what we do here basically is we derive it for any cryptographic algorithm, and then we just hash it with curl, and then we get a seed that is a form of, for IOTA. And so the private key that is returned by the ledger is basically just the entropy of the key. And then it gets squeezed for the public address. So this is all these what's called sponge constructs. So those hashes can do multiple absorbs, always with their certain chunk size, and multiple squeezes, even again with their chunk size. And so this is a picture here. You always squeeze in this certain chunks. And as I told you before, a chunk for IOTA is 243 trits or 48 bytes. So the good thing is there's no need to have the private key as a whole. You only need those 40-byte blocks, because then you can use different hash instant and absorb it, and then generate your next block, absorb it again. And this makes it much more efficient, because such a hashing context is about 400 bytes. So as I told you, you need two of them. One of them basically squeezes out the private key, and the other one, always in the chunks, and the other one just absorbs them as they come. So you have 400 bytes, and with everything else that you might need to get it working, this is 1K for the address generation. And when using the hardware version and doing some tricks here, so it's actually an issue, because after every hash call you have to unset the stupid last trit. And this can be done really easily if you have a trit-based processor, but for binaries you need to re-implement this in binary arithmetics. Which is kind of possible, because it's just like adding like 3 to the power of 242 whatever, and you can actually store this number as a constant. Because fortunately, constants, if you have a static const, they do not count to your RAM. They are part of the program code, and so you can use much more of those. So with this combined with the hardware hashing, we got it to about 2 seconds for one address generation. For level 2. So it's about 1 second, a little bit more for level 1, and 3 seconds something for level 3. But as I told you, I'm sticking to level 2 here, which is about 2 seconds. So now we have our address, and now we want to do a transaction. A transaction always comes in bundles of multiple transactions. And they're composed as follows. The first one is the address. An address is the result of a hash, and that's exactly this 243 trits. Then you put the value, so the amount you want to transfer, so either plus or negative, encoded in 81 trits. Then the tag, this is also this small tag you have, it's also again 27 tries or 81 trits. Then you have the index of the transaction, 27 threads, the last index of the transaction, 27 threads, and the timestamp, 27 threads. And this adds up to 243, and it must, because we always need to work on chunk sizes of 243. Everything else is not working, so they designed it just in that way that you again get this 243 threads. So, and each transaction then is absorbed one after another and then squeezed for the hash, and this is then the so-called bundle hash. And so far so good. That sounds really awesome because we can do the same thing again. We can take one transaction at a time, absorb it, discard it, get a new one, discard it. But unfortunately, this does not work because there is this issue that there must not be an M, so the highest value tried in a normalized hash. This is for security reasons. So there is a bug in the code, more or less, that would completely disclose that chunk of a private key if you get that value in the normalized hash. It can be easily fixed. You just need to take this chunk and hash it again once. It's really trivial, but it should change addresses and stuff like that. So far the foundation hasn't done that. I don't know why they didn't do it when they changed the hashing algorithm anyways, but so far it hasn't been done. And so you always have to check, you have to basically do a little proof of work there, because you have to check whether your hash contains this M, and if it does, then you just increment the tag of the first transaction, rehash everything again, check is it now without an M again, and so forth. So unfortunately, this is the tag of the first transaction. So we must keep all those transactions, we must store them so that we can increment the first tag and then hash everything again. So, but this is still not too bad, because if we say we want to allow up to 10 transactions, this would be 1K of storage, which is kind of more or less okay. And then this would lead, you need, for every input, you need 2 transactions, because this is the security level. If you had level 1, it would be just 1 for 3. So for example, you could have like 2 inputs and then 6 outputs. So this is a reasonable size to have 10 there. So this is not such a restriction. Okay, now we have the bundle hash, and the last thing to do is you have to sign the inputs. And what IOTA uses, they use this Internet signature scheme with a chunk size of 1 tryte, and it is normal. It uses a normalized hash, which has the advantage that no checksum is needed, and this results in about 2,000 tries per transaction signature. And but fortunately, we can do something again so that we can produce this part by part and not as a whole. And if I bring up this sponge hash construct again, so we basically already had this here. So we can absorb one by one, but we can also, of course, squeeze one by one. And the best thing is, for IOTA, or for curl, to be better, this F here is really trivial, because what it basically does, it takes the result of the last digest, so basically the last one we put out here, it completely resets the hashing, and then just flips every byte and absorbs it. So we just need to store basically this array here, which is 48 bytes, and then we can reinitiate the curl at any point and extract further, or squeeze further chunks there. So we don't even need to store the whole context, which is about 400 bytes, which is still pretty big. We just need to store 48 bytes, and then we can initiate a completely new context after we transferred everything, got it out of our system, initiate a new context based on those 48 bytes, and then work from that again. And so so what one could, for example, do, so the interface is not quite ironed out yet, so you could, for example, do 9 fragments of 240 tries, and this roughly takes, for security level 2, 1 second. So for every input, you have 1 second you need to compute. So this is more or less reasonable. It's slower than for Bitcoin, obviously, but it's doable. So when we started out, we had like minutes there. So, but now with seconds, you can actually work with that. So, what is our current state? So we have a working proof of concept implementation for all those parts I showed you. So we can generate hashes, we can generate addresses, we can sign transactions. But what's currently missing is the complete I/O and the interface for that, how the commands get into the ledger and stuff like that. Also, a web wallet is there, or some integration, for example, into Trinity or something else. And then another issue is you need to get accepted by a ledger. So they have a reviewing process. You pay a certain amount to the company behind Ledger. They review your code, and then they sign it, and you get into the official manager app or whatever they call it. So this still needs to be done, obviously. And then also what I called here baby proofing. This is actually quite an issue, and this is one of the fundamental differences you have for IOTA based to basically any other coin. And the issue is this key reusage. So because of this Winternitz signature, which has the advantage of being like quantum safe, you must not reuse it, as always part of your signature gets revealed with every signature, and you must not sign with a certain key twice. And this makes actually a huge difference, because it is trivial as a malicious host program to trick the ledger into generating an invalid transaction. For example, it can say this input address, you just have an amount of 2 on it, and I put out the transaction with 3. So then usually you see, do you want to transfer, the output amount could be correct, but the input amount would be wrong. And then you'd produce an invalid transaction. That would be absolutely no issue for Bitcoin, for example, because then the network would just not accept it, and there would no incentive on doing that. But for IOTA, that is different, because the network still does not accept it, but you, as a malicious host program, you get parts of the private key revealed. So you maybe need to do that 2 or 3 times, and then you can brute force the key. So this is an issue, and there need to be certain steps taken to ensure that this kind of does not happen. And it gets even worse, even if your wallet is working 100% correct. If you're working behind a malicious full node, it can give you wrong balances on your accounts. It tells you there are 10 IOTA on this address, but there are just 5 on them, so you'll always generate an invalid ID, and then the full node gets a transaction and can maybe do something with it. And also, if you, for example, use a second ledger initiated to the same seed, so for example, you say you want to have a backup ledger locked up in a safety deposit somewhere, so you initialize them with both the same seed, then you could potentially generate a transaction from the same address because they are generating or referring to the same index. And so there are basically 2 things you can do. The first one is rather simple and not convenient. So on the display of the ledger, it must always say, are you sure you want to transfer from this input, from this address, it must be even the address there, you want to transfer 10 IOTA. Are you sure that this is the correct address? And are you sure that this is the correct amount? Are you sure that you have more than this on this address? And this needs to be done for every input, and of course for the output, and potentially even for the change address where you want to send the changes. So it's doable, but it's not very user-friendly. Another way would be that the ledger keeps track of the index. So for example, the ledger somehow keeps just only one active address, and it just does not let you generate any other transactions just from this active one. And if you transferred funds away, it always must be the full funds. So it's a little better, but it still is. If the balance are wrong, because the ledger can't also keep track of the balances, they always rely on some node giving the full balances there. And then you also come in other problems. For example, due to some hardware malfunctions, the transaction is actually completely generated on the ledger, but for some reason does not get back to your computer. Then the ledger thinks, okay, you already spent the money, but you did not. So you want to somehow regenerate the old one, and you can't because the ledger thinks you're at a different address. And this is also a fundamental difference, because this usually for all the other applications, the ledger is stateless. So it doesn't know anything about your wallet, your funds, your active stuff. It gets everything from a wallet. And this for other currencies is a reasonable approach. It is safe. But for IOTA, it actually might be an issue. Yeah. So we are basically, you can find us under the following Discord. And of course, if you want to buy us a beer or something like that, I put the address down here. So, are there any questions? Yeah.
I'm currently also trying to getting IOTA done on C, which seems to be not that easy because this one only available more or less by the IOTA Foundation. Okay, I mean, it's one guy who's now working at the IOTA Foundation. Is not up to date anymore. Just this. The Kerl with E says that you should use, or you need to use KICAC 384, I think. But one simple question. Before it was specified in SHA-3, there were different specifications. Is this KICAC, what curl means, KICAC 384, exactly the same like the SHA-384?
No.
It's a different one.
From a mathematical point of view, they're almost identical. Okay. They're the same theories behind them, but they produce different hashes. So
yeah, that's the question. Okay, it uses different rates, capacity, and
yeah, it's the same theory, sponge constructs, and same parameters,
but you can choose way different configurations how to.
Exactly.
Can you maybe send me the specification for this one, because I couldn't find anything. I just found this new SHA-3.
There is even they have a pretty good curl specification from the IOTA Foundation.
With you?
No, the new one, where they give they reference the reference implementation of this KECAC, whatever how do you pronounce it, and they also give some test vectors, and they even give some pseudocode how you're supposed to convert the ternary into binary.
Yeah, but for the SHA, it's just I used I forgot which library I used, but I have to provide the rate, the capacity, and I couldn't find which values I have to use.
Yeah.
So is it also?
It should be there, or you. So actually, what we have as for our testing framework, we have a testing framework for that runs on a regular computer, so we can do like a continuous integration tests and stuff like that without having and the ledger plugged in, and it basically mocks those functions. So those hardware calls that on the ledger you'd use those system hardware calls, and it basically mocks them with this reference implementation. So we're actually using that. So we have more or less a working C implementation on a regular hardware.
On 32 bits also, and 8 bits.
What do you mean?
Yeah, does this implementation also work on 8-bit, like the AVR?
No, it does not. So you could so it's the big. You need to have those big integer arithmetics. And in theory, you could, of course, implement them in any bits or chunk size you want. We use 32 bits for that because it's the fastest on the Nano. So currently it needs 32 bits. And I don't know whether the SHA reference implementation, whether it worked with 8 bits or whatever. I don't know.
They have, the curl is referencing to one C library, which I also actually using, I mean the KEKA. And they have a compiler option for AVR CPUs, processors with 8 bits, so I guess...
Yeah, well, in general, you can, of course, translate like also 64-bit arithmetics to 8 bits, so yeah.
They have also assembler code for it, so I guess they optimized it for it.
I don't know.
Makes sense.
Fortunately, the ledger has even 64-bit arithmetics built in, so...
And another question about calculating the tries. Some people told me in the Discord the trick with, or just the sentence, 1 byte for 2 tries, which works, and it's simple to implement. But also somebody told me that there should be also a way with just bit shifting instead of using this array solution and going over the array and find the right character that you have to use. Do you use this bit shifting solution?
Yeah, we compressed it as much as it can because we are discarding even the last trit. So we're compressing it to 48 bytes, and this is the best you can mathematically do. So, but this, of course, only works then that you need binary arithmetics for that. At certain points, you more or less need to convert it back to trits, but we try to get everything that there is into binary. For example, as I told you, this adding a certain trit, it just corresponds to adding 3 to the power of 200 something to your binary number. You just need to encode it as big Indian, for example, and into 32 byte chunks, and then you can use that. So I doubt that you could get more efficient than that. Because we basically completely left the trinary where possible. We moved to binary, so yeah.
This might be a very naive question, but you mentioned that the last 2 bits of the KEKA hashes, they're thrown away, so they're discarded. But that does not compromise the hash.
Actually, it's the other way around. The last 2 bits of the input get discarded.
Oh, okay. Yes.
It weakens your hash function, obviously, but yeah, they assume that if you have, I don't know, 48 bytes and just discard 2 bits, it's not such big of a deal. Yeah.
You were talking about that you have to review your code by ledger, by ledger itself. What is that for? So that you get a secure firmware where they say IOTA app is verified, or? Yeah,
now you can go to our GitHub page. You can and then make a make load or whatever after you installed everything, and then it uploads to your ledger. It just says, are you sure this is a non-genuine app? It's coming from the following key. Do you really want to install it? Then you can do it. But it is not in the official store, and you always, if you start the app, you always need to say, this is non-genuine, are you absolutely sure, yes or no? And to get rid of those things, that it's natively built into the store or whatever they have, and that those restrictions are no longer there you need this review process. And you have to pay a fee of, I don't know, 50,000 euros, something like that.
Okay.
So that, yeah.
And then they sign your code?
Exactly.
Ah, okay. So maybe you can use the IOTA ecosystem fund for that, because 50,000 euros are a lot.
It's not, yeah. So we'll see. So currently, as I told you, we don't have the I/O and the API all ironed out yet, but I don't think there are any showstoppers that there could be, because we got the algorithms working, so I don't know. Yeah.
So what is the incentive then to do that, to pay that fee? Will you get reward then if people are installing your software? On the
No.
project?
It's
For
just
fun.
yeah.
But that's an expensive fund, right?
Yeah, I would do it. I hope that the IOTA Foundation or whatever the community
But,
jumps in.
Everybody in the community has then
Yeah.
a secure wallet. Yeah.
Exactly.
Yeah.
So they basically have it so that not everyone goes and say, review my shitty code here, and
Yes,
so they set this, and of
Yeah.
course they need to invest some manpower to review it. So
Yeah.
that's a decision they made.
Got another question about this flaw or this bug that you were mentioning. Is this, so did I get that right? That you basically have to keep track of every tag during this proof of work that you're doing there, or what was that bug again?
Yeah. So the bug was that the hash must not contain the maximum trig value, which is plus 13 or m.
Yeah.
And
That's the proof of work.
and that's a
right?
proof of work.
Yes.
And by definition, you just add 1 to the trinary representation of the tag of the first transaction.
Mhm.
And then, of course, your entire hash changes, and you check again whether it contains this m, and increment again. So this is kind of a proof of work, but not intended one.
Okay. Did you communicate this already with the?
They obviously they know it, and come from beyond. He even fixed it in his own repository.
That's what he claims.
No, it is fixed.
Yeah.
It
Okay.
is, no, you can look at
It's
the
not
code.
implemented in.
No, it's not. It would change the addresses because the issue is with these internet signatures. What you do is you basically take the value. You look tryte by tryte at the hash you get for your bundle hash, and then you say for plus 13 you hash it 0 times. For plus 12 you hash it 1 times, and so forth. And the issue is you hash it 0 times for plus 13. If you'd hash it once for 13, everything would be fine.
I see. Yeah. Yeah.
So it's trivial to fix. It's even not a big issue. It's just if some potential future issues with the hashing algorithm are found that this is vulnerable, because you could maybe derive the squeeze. You could maybe get the next block out of this if you have exactly that one. So for security reasons, you must hash it at least once.
So the tag value is unusable.
They have something. They have a tag and an obsolete tag, and they even but you mentioned they're completely planning on redesigning this transactions whatever and getting rid of that. And it's also an issue with the hash normalization. You need the normalized hash for some mathematical reasons, and so you basically change the hash until it's normalized, which again makes the hash much weaker. So they're planning on changing that too. That you have actually some actual proof of work in there. So you have to regenerate your hash until you find one that is normalized from the input you get and stuff like that. So this is going to change drastically. But it's not, as usually it's not communicated how and when and if.
With normalization, you mean this stuff while the proof of work where you fill up with zeros, or?
No. So as I told you, so for this internet signatures, you hash it basically multiple times depending on the value you have. And this means obviously that for every future hashes, so if you have if you hashed it 0 times, then it's trivial to find out how it would be after 1 hash, because you can just hash it once and check it. But what's infeasible, if you have the hash for, let's say, value 5, you don't know what it's for 4 or 3 or 2. You just know what's for 6, 7, and so forth. So you always disclose all the values that are above the ones you had in your key. And if, for example, your key, your non-normalized key, would consist of all m's, you would be done, because this is completely the private key. And so this is a very, and if you normalize it, you're sure that exactly 50% of the key gets disclosed. So then you have mathematical properties that you need some, I don't know, like 4 or 5 signatures to make it trivial to crack the hash after 4 or 5 disclosures, 4 or 5 signatures. And if you do not normalize it, it would be random. It could be that you don't reveal anything more or less, or it could be that you reveal almost everything. So they just take the hash, normalize it, so that exactly 50% get disclosed. So, if there are no questions, I have someone. So we are kind of discussing the last point I had there. What we want to do there. Whether we want to have this expert mode where you can say the ledger, give me address for the following index, no matter what has been done before, stateless, and also for transactions, sign this transaction with these inputs and these outputs. Sign it for me. This would be the one option, or the other option is to somehow keep track of the index, but these would have severe limitations. For example, just one input and one output for a transaction. So, any input from you guys? What?
If I understand it correctly, so the second method, you will have to store how many IOTAs are in my wallet. Maybe. So
Yeah,
that
kind of. Or at least if the positive amount or
yes,
yeah.
yes. But I think if I have a ledger, then I will only use this, and I don't. I will not use the IOTA Light wallet to send money or something like this. So I think for me it's no problem if it is stored in the ledger. And if I lose my ledger, okay, then I have to check if my full node is giving me correct balance. But I think it's okay.
But it would have limitations. For example, if you lose your ledger, the reinitiation would be much harder. Because
yeah, you have to enter how much IOTAs do you have and what is the index.
Yeah, but then it needs basically, if you're at index 100, it needs to check every index up to 100 because
Yes.
you can't tell them, I know, I lost my ledger at index 100.
Yeah.
Get me back there. It just does not. You must, because then you must follow this recovery protocol and starting from 1 and so on. So
Can't you enter in the ledger that index 100 is active right now?
yeah, but then again, you could compromise it by entering an index that has already been used for spending some funds. So this is again this
Yes.
trade-off there.
Hard to tell.
Yeah.
Can there be a full node that is trusted? So maybe that there is a full node that signs the transaction, the values, how much IOTAs are in the address to the ledger, and that verifies, okay, this is my trusted full node, and I accept these values.
Currently, there is no official functionality for that.
Yeah, I know.
And I think that there's so much that needs to be done especially for transaction addresses by IOTA, because they use their own thing. We have things like BIP44 and stuff like that, and they still use their own indexes. So things have to change there. They need to develop a standard, how addresses are derived, and how you keep track after snapshots. That's also an issue.
Yes.
So
Is there communication between you guys and the foundation?
A little bit. So Peter, he actually worked on the Flash network as part of or under the foundation. So he has still a pretty good contact to those guys, but nothing really official. So they don't tell us more than they tell anyone. We have now some connection to the Trinity wallet to get something going there. We'll see.
So what's your roadmap? Or what are your plans? What are you still trying to achieve down the road? Or what are you kind of needing to wait for to be done?
Yeah, so we kind of shifted our plans there. We now want to get a good interface there that can be used by third-party wallets. First, we decided to do our own easy web wallet or whatever, so that people can actually start using it. But as Trinity is pretty close, we decided that that does not really make sense. We'd rather work on a proper interface that can be used by a third party right from the start. So this is the first things we are currently working on. And then, of course, getting everything signed by the foundation is the next step, by the ledger.
Do you have to re-sign if you make firmware changes?
I don't know exactly how that works, yes, but they told us this is just like a 1 or 2 day process, so...
Okay. So they look at the changes?
I don't know how exactly but yeah.
Then they want just 25,000 euros.
Oh, we changed everything.
So, and actually a lot of changes are coming. For example, I have no idea whether that would still be feasible for curl, because there's no hardware acceleration for curl, for example.
But
So,
there will be.
yeah, but not for the Ledger Nano, obviously, yeah. So if they make a lot of changes, and even this, I have no idea, this tiny POW they may be introducing, no idea. If that takes minutes on the ledger, it's not feasible anymore.
Yeah.
So currently it's pretty good, but if they make changes, it could definitely change the whole situation, yeah.
Do you need some help in programming or something like this? Can we help you with some code?
Sure. So, obviously it would be good if you're an embedded C developer. That would be most. So, yeah. So currently, so we just have the backbone implementation done. So we're currently working on getting this interface done, and this also does not involve that much embedded stuff or math, because it's just the usual checking whether input is correct, a lot of testing, what happens for overflows, underflows, stuff like that. So this actually is something we could need help with, or developing a web wallet. We three decided we're not going to do it, but nevertheless, it would be probably a good thing to have one, as nobody knows exactly when the third party's wallets are coming out.
Okay.
Come to the Discord, you are already on.
Linearzahlen.